Why is quantum gravity so hard to understand? Have you ever wondered why gravity behaves so differently at the smallest scales? The question of why quantum gravity is so hard to understand is a fascinating one. To grasp this, we need to look at two major theories: quantum mechanics and general relativity. Quantum mechanics deals with the behavior of tiny particles, like atoms and subatomic particles. It explains how these particles interact and exist in a world governed by probabilities. On the other hand, general relativity describes gravity not as a force but as the bending of space and time caused by mass. This means that gravity shapes the very fabric of the universe itself. The challenge arises because these two theories operate on different scales and use different concepts. In quantum mechanics, space and time are fixed backgrounds where particles interact. However, in general relativity, space and time are dynamic and can change based on the presence of mass and energy. This fundamental difference makes it tricky to combine the two into a single theory. When physicists try to apply quantum rules to gravity, they face complex mathematical challenges. The calculations often lead to infinities that cannot be easily resolved. This makes it hard to create a reliable model that accurately describes gravity at the quantum level. The interactions of particles can happen in countless ways, and when you consider that spacetime itself can warp and fluctuate, the number of possibilities becomes overwhelming. Another significant hurdle is the lack of experimental evidence to guide the development of quantum gravity theories. The effects of quantum gravity are expected to be noticeable only at extremely small scales, such as near black holes or during the very early moments of the universe. These conditions are challenging to observe directly, leaving scientists without the data they need to refine their theories. In essence, the difficulty in understanding quantum gravity stems from the need to merge the flexible, curved spacetime of general relativity with the probabilistic, particle-based world of quantum mechanics. The two frameworks use fundamentally different ideas about space, time, and forces. Current mathematical tools struggle to handle their combination, which is why scientists continue to search for a theory that can fully explain gravity in the quantum realm. This quest could lead to a better understanding of the universe, from the tiniest particles to the vast cosmic structures.